kind of problem. Okay, in cylindrical coordinate, which of the following is Hermitian operator? Okay. One thing is you don't know cylindrical, at least spherical polar coordinate we know right now. Okay, because we need some vector calculus idea to solve this one. Okay, or whether we solve during revision. I mean, gradient is required in different coordinates to solve this one. Okay, gradient we have taken in spherical polar coordinate. Okay, maybe I might have written in yeah, Cartesian and spherical polar. Okay, we need gradient concept here. Okay, so to do this one. Now the thing that I want to tell you here is, okay, speak up. Suppose in case of one dimension, whatever px you have, what is this one? Minus I h bar dou by dou x. Okay, py that's equal to minus I h bar dou by dou y. So pz that's equal to minus I h bar dou by dou z. Okay, I mean, I can solve this one, but I want to give you what is the essence of the question. Okay, at least later during revision, when you are good with gradient and all, you can do it again. Okay, so these are all Hermitian, am I right? These are all Hermitian operators actually. Okay, even though you take this operator in 3 dimension, they are Hermitian. Okay, if I say suppose some inner product, okay, pick up some psi star, suppose px cap psi, okay, or I'll write like this, psi star of, okay, x comma y comma z, okay, pick up some px cap of psi of x comma y comma z, dx dy dz, am I right? I mean, in case of 3 dimension, I mean, your inner product, that will be dx dy dz, isn't it? I'm talking about 3 dimension here. Okay, pick up, this is a triple integral actually. Okay, operating operator to pick up second member, okay, that's equal to operating its Hermitian conjugate to first member. That Hermitian conjugate is itself, actually it will come as it is here. And the main what you call reason for that is there is nothing here, am I right? Dx dy dz, there is no x or something. But in case of polar coordinate, d tau that contain r square dr, am I right? Do you remember? So that play very important role actually. Okay, speak up. Here what you can do one integration by parts and you can take it here, isn't it? That's what we did. That's how we proved the Hermitian conjugation actually. You can do one integration by parts. But in polar coordinate, one more r square dr would come, right? When you take integration by parts, something else would happen actually. Speak up. So that's why this is equal to, so I can write like this, px cap dagger, that is itself, okay, psi of x comma y comma z, okay, whole star, am I right? Operating operator to second member is equal to operating its Hermitian conjugate to first member, psi of x comma y comma z dx dy dz. Is that okay? Speak up. Now what I'm saying is, I mean, if it is Hermitian operator, okay, speak up, wait a second. If it is Hermitian operator, operating operator to second member is equivalent to operating the same operator to first member, isn't it? So this is true in case of Cartesian component of momentum. Any of the px, py, pz, whatever you take, this is true actually. You can just write dou by dou x, and you can do one integration by parts with respect to x. You can show this one. You leave y and z integral as it is. You leave that part of the integral as it is. Okay, you don't do that integral. You do only integration by parts in x. You can prove this one actually. Okay, but the same thing is not true if I define. So pr, I'll do in polar coordinate. Okay, pick up. Later maybe you can do in cylindrical coordinate. Let me do the, I mean, very similar problem in spherical polar coordinate. Okay, if I go to spherical polar, okay, pick up. I was talking about Cartesian here. Okay, speak up. I was talking about Cartesian here. Wait a second. Okay, this is the problem. I was talking about Cartesian here. Speak up. Cartesian coordinate. Okay. Your operator corresponds to component of momenta. Can I say like this? Okay. Speak up. So if you go for spherical polar, okay, speak up. So if you define PR especially, okay, speak up. So I will come out with better idea, maybe. I mean, in classical mechanics, if I think in this manner, I may get some idea, okay. Minus IH bar dou by dou R, okay, speak up. Wrong. It won't work. Speak up. It is not Hermitian at all. Can you guess why? Speak up. When you do that integration by part, something else would come to the left part actually. Speak up. I mean, if you just do this one, okay. Speak up. What is this one? Psi star of R theta phi, okay, into minus IH bar. Pick up. Dou by dou R of, okay, psi of R theta phi, okay. Speak up. R square dr, sine theta d phi. Now it's not straightforward integration by parts actually. R square is there, including that. I mean, with respect to R, suppose if you are doing only R part of the integral, okay, leave theta and phi later, okay, I'll leave theta and phi later. I'm doing 0 to infinity, speak up. So psi star of R theta phi, okay, so minus IH bar, I will take it outside, okay, so dou psi by dou R of R theta phi, okay, speak up. R square dr, am I right? Phi R square dr, okay, speak up. You do this one, sine theta d theta d phi. Are you getting fine? So now again, it gives some issue. Is that okay? It gives some issue. I mean, how do you do integration by part? That itself is headache. Am I right? You have R square. Three functions are there actually. Okay, speak up. You may need to take R square into this side together, and then you need to do integration by parts. Again, you can't make this derivative to come here because of this R square. I mean, that's how we did actually. Okay, speak up. I mean, integral, okay, psi star dou by dou x psi dx. Okay, we took one integration by part because at the boundary our wave function would vanish. First term of the integration by parts was 0. Okay, speak up. These were the argument that we have done actually. Speak up. But we can't do the same thing because of that factor R square. And one more thing, I don't know whether this will vanish at 0. Need not be, isn't it? 0 is not a boundary. Spherical polar coordinate origin is not a boundary. Boundary means end point, isn't it? It is bit different. Okay, the whole problem is bit different. I had some other idea, now I can't recall. But what we can do is, this is not Hermitian. Okay, speak up. But what we can do is we can form a Hermitian operator like this actually. Okay, speak up. We can form a Hermitian operator. I mean, I did solve this one earlier. I mean, somewhere I found this idea from MIT Open Coursera. Okay, I mean, in our textbook it is not there. So it is like this: PR that's equal to P vector dot R cap. Okay, R cap is unit vector, not operator, plus R cap dot P. Okay, so divided by 2 actually. Actually, somehow you should able to prove that P cap dot R cap, it is not Hermitian. Okay, but this one is Hermitian actually. Pick up. This whole operator is Hermitian. This kind of problem is also there. Right now, I don't have that problem again. What was that problem? So this one, okay. Okay. So classically, you have some Hamiltonian that's equal to x into p. This was the problem, okay. Classical one, x and p are variable here. You need to construct quantum mechanical operator. What would you do? Because x into p is not Hermitian actually. X px, okay. This is a classical Hamiltonian. Is that okay? This is a classical Hamiltonian. Okay, speak up. So now, okay, classically this can be Hamiltonian. X is some real variable, px is some real variable. But if you write quantum mechanical operators, pick up x cap, px cap. Is that Hermitian? It's not Hermitian. Why? They do not commute. Am I right? Product of two Hermitian operator is Hermitian only if they commute. They do not commute. Okay, pick up. So that's why to form quantum mechanical Hermitian operator, what gimmick I do is I'll just write x px plus px x by 2. Now if you put cap, pick up x cap px cap plus px cap x cap. Okay, don't take the derivative. You need to operate it on something. Okay, don't take the derivative and write 1 here. Okay, I mean, pick up. Be careful while using this operator 2 here. Okay, so can you just note down this one? Pick up. Is that okay? Very similar idea that I'm proposing here. Is that okay? Pick up. Very similar idea. So this p vector dot r cap. Okay, that's not Hermitian, but this is Hermitian actually. Speak up.
You're taking some average or something.
No, I mean how to prove. Let me think over it, okay? Because bit very new one. I mean, in our textbook, it is not there. I found it from MIT courseware, and I again. Speak up. Now this p vector is nothing but minus I h bar gradient. I'm doing in spherical polar. Okay, they are asking in cylindrical coordinate. Okay, speak up. This gradient in spherical polar coordinate, that is r cap by 1. I mean, why I write 1 is my practice. Okay, we call this as hr, h theta, h phi. I mean, like that. Okay, we shall discuss more in electrodynamics. Okay, dou by dou r. Okay, plus theta cap by r. Dou by dou theta. Okay, plus, I mean, this may be new for you. Dou by dou theta plus phi cap by r sine theta. Okay, dou by dou phi. This is gradient in spherical polar coordinate. Is that okay? If I take a dot product with r cap, I hope you can get what would you get here. Am I right? If you take a dot product with r cap here, okay, pick up. But you should be a bit careful while doing this whole stuff actually. Pick up. So now to find this operator, okay, speak up. To find this operator, again, as I always suggest, you better to operate it on some dummy function, then remove that function. Otherwise, some mistake will happen actually, because just like here, am I right? By operating in this dou by dou x on x, you may write 1 into minus I h bar. Am I right? That would be wrong. These two together, it is operating. What do you mean by that one? X cap operate first, after that px cap operate. Okay, speak up. So now what I'm saying here is, okay, what I'm going to do here is in the, I'll take in the next page. I'll take in the next page. Speak up. I'll operate this PR on some dummy function. That's r theta phi or something. Okay. Speak up. What is this PR? So r cap. Speak up. What I have written? P vector dot r cap. What is P vector? Minus I h bar. Okay. Del dot r cap. Okay. Operating on f plus what is this one? R cap dot p. Okay. Speak up. So r cap dot minus I h bar del. Okay. Speak up. Operating on f. 1 by 2 I will keep it outside. Speak up. 1 by 2 I will keep it outside. Speak up. So now this is nothing but, okay, so I think I can take minus I h bar outside. Pick up. Minus I h bar outside by 2. Okay. Pick up. So now, so this is nothing but gradient dot, speak up, r cap f. Can I write like this? R cap f. Speak up. This one. So plus, okay, this is nothing but I minus I h bar have taken outside. R cap dot gradient of f actually. It's a kind of divergence. Okay, divergence, vector calculus divergence actually. Speak up. Minus I h bar by 2 that I have taken outside. Okay, I have done here in cylindrical coordinate, but I'm trying in a spherical polar coordinate. Speak up. So can you do this one now? Minus I h bar by 2. Okay, when you do this one, here also bit tricky step may come. Okay, What is this one? R cap into F, am I right? I think that is simply divergence. How do you write the divergence in spherical polar coordinate? Again, this is also required. Divergence. Speak up. Divergence of a vector field in spherical polar coordinate. Any idea? 1 by r square sine theta. Am I right? Right? 1 by r square. AR. Am I right? That's right. Now, if you take this one as a vector, actually, I mean, it requires vector calculus, okay? Idea, okay? So this is only R component, actually. I mean, if you take this one as a vector field, okay, A is equal to R cap into F, okay? So that means plus theta cap into 0 plus phi cap into 0, actually, okay? That's how you have to see. Is that right? Sure. Okay. If this is right, then what I can do is, okay, PR into F, that's equal to minus IH bar by 2 minus IH bar by 2. Okay. Speak up. So this whole thing, uh, 1 by R square, okay, dou by dou R of R square into F. This whole factor. Are you sure R square or R? Yeah, check that out if you are holding Griffiths, okay? Speak up. So plus this is bit simple, I hope. Am I right? Speak up. This part is, I don't think that's much difficult. Am I right? You can write R cap dot. What is this one? R cap by 1 dou F by dou R. Okay, that's right. Is this right? Okay. So plus, I mean, theta cap by R dou F by dou theta plus phi cap by R sine theta. Okay, dou by dou phi of F. Okay, speak up. So now if I do this one, speak up, minus IH bar by 2. Okay, so these are orthogonal coordinate. R cap dot theta cap, R cap dot phi cap, that is 0 actually. Okay, they are orthogonal coordinate. So that's why only first term will remain. The whole thing is 1 by R square dou by dou R square F. Okay, speak up. So plus dou F by dou R actually. Speak up. Now you better to do this differentiation. Pick up. Minus IH bar by 2. Okay. Pick up. What is this differentiation? 1 by R square. Okay. R square as it is dou F by dou R plus F as it is. Pick up. 2R. Okay. Pick up. F as it is 2R plus dou F by dou R actually. Okay. Pick up. I hope when you multiply individually minus IH bar by 2. So R square got cancelled. Dou F by dou R. Okay. Plus 2R into F. Am I right? Plus dou F by dou R. Can I write 2 times? I think this is right.
So 1 by R square will get multiplied to that also.
Okay. Here it will be multiplied to this one. Am I right? By R square. Then I think this 2 got cancelled. Okay. Minus IH bar. Okay. Can I write like this? Dou by dou R plus 1 by R. Operating on F. Check this out. Am I right? Now somebody search in Google radial momentum operator in spherical polar coordinate and match up whether it is right or not. Okay. Radial momentum operator. Maybe in the outside the textbook he might have given this problem either in this one, Titili or somewhere. Okay. Radial momentum operator in spherical coordinate. Yeah, that is right. That is right. Now you need to construct. It's not called as a radial momentum operator in cylindrical coordinate. Yeah. What does this coordinate called in cylindrical coordinate? Speak up. Okay, where is my question? Deleted. Okay, here. So this is for cylindrical coordinate actually. For cylindrical coordinate, something different will happen. Okay, pick up. Don't choose the same thing as that one actually. Okay, which of the following is Hermitian operator? You leave H bar. I should be there. Okay, rest of the thing you collect. Speak up. So I mean, this comes in that theory. Okay, now how do we solve this one without getting into that theory of constructing Hermitian operator? That we shall see. Okay, speak up. I hope in this integral only you can do something. But it's quite hard to predict that one. Okay, in this integral, how it can be done and all. Okay, or if you put this one in this integral. Okay, if you put this operator in that integral, if you do integration by parts. Okay, pick up. You should come to the first member. You should able to observe, just like we proved px cap is Hermitian operator. I think that is bit lengthy than this theory, doing integration by parts and proving that which one of the following. I mean, how will you do trial and error? That's not what you call feasible. Okay, I mean, what people will do after generating key answer. Okay, after they generated key answer, they will try to do in that way actually. That's not feasible. Are you getting my point? You know the answer, then you can prove that it is Hermitian by doing integration by parts. That's not a feasible way. You better to work out this theory. Okay, it is there in MIT OpenCourseware. I will share the PDF if possible. Okay, speak up. This is a way to construct a radial momentum operator in spherical polar coordinate. The same thing goes for cylindrical coordinate. The same thing goes for cylindrical coordinate. What you have to do? Speak up. In cylindrical coordinate, okay? So first you define del in cylindrical coordinate. Anyone? S cap divided by 1 dou by dou s, okay? Plus both gradient and divergence formulas are required, okay? Pick up to do this whole problem. Okay, plus I think pi cap divided by s dou by dou pi plus z cap divided by 1. Okay, I mean, why to write this one again? You will understand later. Okay, speak up. Dou by dou z. This is your del operator. Okay, if you wish to find the gradient. Okay, speak up. Then what this coordinate is called? Speak up. Axial coordinate? No. I mean in cylindrical coordinate. In spherical polar coordinate, that's called as radial coordinate. Am I right? Pick up. What do we call in cylindrical coordinate? This one? Axial distance. We say like this. Perpendicular distance from the z axis. Okay. Pick up. If you take a cylinder, I hope it's called as axial coordinate. I don't remember right now. Okay. Pick up. Whatever. Okay. I mean PS again the same thing. Okay. S cap dot P vector. Okay. Pick up. Plus P vector dot S cap whole divided by 2. This will be Hermitian. Okay. What it called? Okay, he didn't name. Okay, we shall see that one. Okay. Pick up this only S cap dot P. Okay. This is not Hermitian. Unlike in Cartesian coordinate, you write I cap dot P, that's equal to Px. Am I right? This will be directly Hermitian in Cartesian, but it will not be Hermitian in spherical or cylindrical. You need to do this one, very similar step. Okay, you will end up with the answer, right answer. Okay.